This video discusses the solution to question 39. For the dual slope ADC in figure 6, assume as before that for a fixed number of cycles N1, the input signal Vin is integrated. After that, for a variable number of cycles N2 minus N1, the negative Vref voltage is integrated. Assume that N1 is 1024, f clock is 1 MHz, Vref is 2 volts, and Vin lies between 0 and Vref. The integrator block can be modeled as this given integral here, where Vint is the output of the integrator and Vx is the input of the integrator. Tau is 1 millisecond. Determine the maximum voltage Vint that can occur in this converter and the maximum total conversion time. For this question, it is important to remember that even though the period of the first phase is fixed, namely from 0 to n1 clock cycles, the slope is wholly determined by the input voltage. The larger the input voltage, the larger the slope and therefore the larger the peak voltage that we will reach. It has been given to us that the integrator voltage follows this integral over here and that the input voltage lies between 0 and 2 volts, namely the reference voltage. So we will reach the maximum integrator voltage at a time of n1 over f clock, and we can fill that into the equation above, as well as an input voltage of 2 volts. And with the given parameters from the question, that yields us an integrator voltage of 2.048 volts. Secondly, we know that the maximum input voltage is minus the reference voltage. Since the slope in the second phase is fixed and is wholly determined by minus 2 volts, namely that reference voltage that we integrate, we know that the second period will have the same length as the first period, and therefore n2 is 2 times n1. So the conversion time will be n2 over f clock, and since n1 is 1024, we know that this total conversion time is 2048 over 1 MHz, and that gives us 2048 microseconds.